Welcome to our tutorial on table extraction and understanding for scientific and enterprise applications. So my name is Doug Burdick, and I will be presenting this tutorial along with Alexandre, Nancy, Giannis, and Marina. So we are all affiliated with IBM Research, specifically the Albany Research Center in San Jose, California. So I want to just start by giving the tutorial outline. So first, I'm going to present the introduction where I will define the problem, what we mean by table extraction and table understanding. And then hopefully I'll spend some time convincing you that this is a challenging and interesting problem to consider. Then subsequently, we will have more details about table identification, what work has been done in that area. Also table understanding as well, and then putting everything together, how this will work together for an end-to-end table processing pipeline, for instance. And then also the applications that can be built on top of the output from table processing. What do we do with the tables? And then finally, concluding remarks. So for the introduction, I want to begin by precisely defining the problem. This is an area where there has been a tremendous amount of work done over multiple decades. So I want to begin by level setting what we define these problems to be. So, tables are a popular data representation, and we see them in many different forms and many different document types and domains. So we have invoices, scientific papers, loan agreements, possibly financial reports that you look at. And there's a simple reason for that. Tables are an extremely compact representation of a lot of information. And it's also in a form that is easy to understand for humans. For machines, that might be a slightly different story to do, say, an automated understanding. But for humans, it's pretty easy. I want to start with a simple end-to-end example. So if you look at the table on the left, the value in the red box, what does that value, that 672 in that table mean? The full English sentence definition of that would be the net earnings for 3 months ended July 29th, 2017 were 672 million US dollars. So if you went through this exercise, whether you realized it or not, you subconsciously went through the following steps in this order, probably. So first, you found the location of the table on the page. Then your eye found the values aligned in that column that had the 672 in it. And then likewise, it went horizontally across the page to find the values in the corresponding row. Then for those values that were aligned, you broke them down into two different classes. So there were, say, body values, and then there were header values, or values, the header values which describe the other values in that column or that row. Then, your eye went around and you normalized those values using additional context that was available. So for instance, the $sign and in the upper left corner, the millions except per share data in the yellow boxes, those provide context that 672 actually represents 672 million US dollars. So those first three steps we refer to as table extraction. How do we identify the table location and the structure of the cells inside of that table? Then the final two steps we refer to as table understanding, which provides semantic context to the table values. So just to kind of be a little more precise. So for table extraction, we start with the input document in its native format. So this could be an image, a PDF file, or an Office document. And then we convert it to an output representation of the document contents, which includes the tabular information that was identified. So we have the table border for each table, the partitioning of the table contents into cells, and then also both the vertical and horizontal alignment of cells has been identified as well. Now for table understanding, the problem, so we start with our input is the document contents with the tabular information identified. So maybe it had to go from an extraction step, or maybe you just got it for free, depending on the document format. And then we want to convert that into a representation that both captures the semantic information and is amiable to post-processing downstream. So one example of that output might be something like the JSON, for instance, I'm showing on the right. So in that JSON, you see during table understanding, the headers for the columns and the rows had been identified, and that they are now associated with each cell value. So for instance, the 206924 in the blue box on the left, that cell is actually represented by that snippet of JSON in the blue box on the right, because you have the row and column header cells are associated with that body cell. Another alternative representation might be of a more relational flavor. So for instance, you will have multiple tables where each row corresponds to one of the body cells of the original table. And that row in that table has all of the additional semantic information provided by the associated headers. So it's capturing the same information in a different format. So now that we've kind of gone through the definition of what table extraction and table understanding are, now, well, I want to get into why this is a challenging problem. And this is something that might not be necessarily apparent. Now, don't you get this from HTML tables? And most document formats already have this, like Office, I can just save it as HTML and so forth. The answer is there's a spectrum of how well the table structure is represented across different document formats. So you can go from none at all, where there's no information, to a complete representation where you have both the structure and the cell contents represented. So here's a listing of popular document formats, and you can see where they fall on this spectrum. And we're going to go into more detail in the next few slides about these different formats. So I just want to also level set. The statement I just made pertains to table extraction and the representation of the structure in those native document formats. Table understanding, however, is still required for all document types. So if you start with a native document, you will still have to do table understanding, even for HTML tables, for instance. And of course, you can see the cited work on the slide are examples of table understanding being applied to those document formats. So if we look at HTML, we have the complete representation of both. So we have the border of the table has been identified, and we also have the cell structure with its alignment. Now we go to, say, Excel spreadsheets. It depends. And it depends on how the author created the document. So for instance, if you put each sheet on a separate table, then you have a complete representation. However, sometimes you may put multiple tables defined on the single Excel spreadsheet. In that latter case, you actually have to go through some effort to identify where one table ends and the other table begins. So that would maybe get a partial score because you have some information, but not all of it. And of course, the cited references or examples of work in that spreadsheet setting. Now for Word, it can range from complete to none at all. So if you use the Office table object for all of the tables, you will get the complete representation of the table and a structure in the document. However, many times people, when they're authoring documents, omit the Office table object and instead they use tabs to align the values. In that latter setting, unfortunately, none of the table structure is represented in that Word document, and it has to be inferred from scratch, effectively. Now, when we come to some other document formats which have no native table representation, an image and text is not surprising because image is just a collection of pixels, plain text is just a collection of characters. And PDF is the one that surprises a lot of people. It was surprising to us when we started considering this problem. And it turns out that PDF, the format, is actually just a collection of instructions to draw characters and graphical elements on that page. So for instance, the PDF in its binary form is just it's a collection of instructions like draw the character M at this position, draw the O, the N, and so forth. Also draw a graphical line from point A to point B. It does not contain any structure information inside of it for tables in the native PDF format. And this holds whether this is a PDF created from, say, scanned images, or even if it's a programmatic PDF, say a PDF that was created by saving an Office document to PDF. This still holds. Now, this is important because PDFs are, if not the widest, arguably one of the most widest used document formats across many different industries, applications, and so forth. And there are 2 to 4 trillion PDFs in existence, according to Gartner, and that number is rapidly growing. And so this widely used document format used in many business and industrial settings, also in scientific settings. The proceedings of this conference will be in PDF documents, have this issue, and that's why it needs to be addressed. Also, there's another challenge though as well. So you don't get it in the native format. And so you begin thinking, okay, how would I design I'll design a deep learning, machine learning based system to actually do the table identification. That is very challenging for the following reason, that there is an extremely large variety in the visual representation of tables in a document. So for instance, when you have tables with graphical lines delineating the cell contents to just a collection of aligned values. You can have complex tables where graphical lines are misleading, and whether this is actually 1 or 2 or 3 tables perhaps. Also, you can have tables interleaved with text and charts. You have to pick out where the table is. Also, you can have very complex tables where you have multiple row, multiple column headers. And also nesting of the row headers, which again is fairly easy for a human looking at it, but is hard to identify what's going on. All of these point to a couple of things. One, you as a human being, and anybody can look at these tables, there is something in common. We, looking at it with not too much time, can infer where the table is if it's not immediately clear, and we can also infer its structure and also even interpret it as well. But being able to build a general model to do that across all of that variety of the visual clues, which can be conflicting when you start looking at documents from different collections and different corpora and so forth, becomes very challenging because those visual features can oftentimes provide conflicting signals. So, I think one of the takeaways, hopefully from this tutorial, will be the following. That there has been decades of work across multiple subcommunities and communities in this area. So information management community, again, this is a broad stroke, has mostly focused on the semi-structured or the structured setting. You're given the table border and the structure, such as HTML tables, or you may have the setting where you have to do the border identification. So this comes to the spreadsheet understanding use case. And the focus has been on the schema inference. What is the schema of the table? Completion, augmenting the schema, also synonyms of values, and also how do we build like table search engines over collections of tables. The document analysis community, so they've looked at this setting, and you see the names of some of the main conferences in that setting. They've focused on the unstructured case. So you have an unstructured text document, and you have to infer the table border and the cell structure, starting from nothing. And they've leveraged rule-based statistical computer vision techniques to do that. And the goal has been around interpreting values of individual tables. So how do you identify table headers and then link those to the corresponding cell values to provide context? Other communities are also have looked at this problem as well. Some communities, say in AI or natural language processing, NLP, the AI community has also started looking at how do you leverage object detection to detect tables from images of document pages, for instance. Also, the NLP community has looked at multimodal approaches. So you start with your classical NLP approaches, and then you augment them with position and format information. And then also, there's a little bit of a focus on complex business documents, tables that have multi-line headers, also column headers that span multiple columns, for instance. And the goal of this tutorial is to synthesize the work across these multiple communities for both the table extraction and table understanding problem together into a unified whole, and then also do that in the context of complex business and scientific documents. Because again, the tables in those documents tend to be very complex, and even maybe a little more complex than a lot of the tables you'll find, say, on web pages, the web tables setting, for instance. And here's just a sample of some of the prior work in table extraction. Don't worry, we're going to go into more detail on this in subsequent parts of this tutorial. But there were, just at ICDAR, which is one of the leading conferences in the document analysis community, there were 16 papers on table extraction alone in that conference, the last one in 2019. So, and for table understanding and its applications, here's just a sample of the work, prior work that will be gone over in the table understanding portion of the tutorial and the application portion of it. Again, this is, if you look at where these conferences and the venues that this work comes from, you have the document analysis, information management database community, also information retrieval, natural language processing, HCI, and AI as well. So it's many different communities have been looking at this problem over a long period of time. And there's still, despite that, there is a great deal of remaining interest and even an increase in recent interest in table processing. And that was the motivation for us to put this tutorial together. This is coming from both the academic setting, so there's lots of papers being published. Again, we have the statistic on the 16 papers on table extraction at ICDAR in 2019, but there has been a lot of other venues have seen an increase in work on table processing and interest. And also even within the data management community. So in 2018, the VLDB 10-year Test of Time Paper Award went to the seminal work on web tables. So that's also indicating a lot of interest even here within the information management community. And also, academically, it's an interesting problem. And even if we start going into the commercial setting, table processing is a key component of many document processing commercial offerings. So you have Amazon Textract and Amazon Kendra, Google Document AI, Microsoft Form Recognizer, and IBM Watson Discovery as well. So again, whether you're in the academic side or whether you're in the commercial practitioner, there's a lot of interest in this area. And just to conclude this section, some brief takeaways from the introduction. Many widely used document formats have limited table representation. So this can come from the limits of the document format. I think the one that's surprising, images and plain text, not surprising. PDF, which is widely used, 2 to 4 trillion of them have this limited table representation due to the format constraints. Also, it comes down to how the document was authored. So this kind of comes into Office documents predominantly. Also, the wide variety of tables makes general model construction extremely difficult. Tables are a form of art. And the diverse visual encoding of semantic information as you go across different document collections makes general model construction difficult, because those features that you would reasonably use to build a model provide conflicting information many times. And then also the different, as you go across different domains. But once the tables have been identified and are interpretable, that enables many downstream applications, which are extremely useful. And we'll be touching on those as well subsequently. So now just a brief recap. So next will be table identification, then followed by table understanding. Then how do we put those together? Just putting all of this together into context for an end-to-end table processing pipeline. And then, of course, the applications that can be built on top of that table processing pipeline. And then finally, concluding remarks. Okay, thank you.